Hey TechnoStuds! In this video, we're going to talk about dynamic routing protocols and specifically the different types of dynamic routing protocols. Knowing the different types can help us choose what would be the best dynamic routing protocol that we would want to use on our network. In this video, we'll start out by talking about all the different types from a high level. Then we'll dig in and talk about what is the difference between an interior gateway protocol and an exterior gateway protocol. Then we'll get into what the difference is between a distance vector and a link state vector. And then finally, we'll wrap things up with a few examples of routing protocols and how they differ. So which dynamic routing protocol are you going to use? Well, that's going to be determined by your different scenarios that are out there, by the scenario of the network that you're trying to set up. So there are different types. Let's go over those different types. So the first thing that's the most obvious here is IP version 4 versus IP version 6. So if you're using RIP version 2 will handle IP version 4 versus RIP NG is going to be IP version 6. So same thing with you have EIGRP and then you have EIGRP for IPv6. You have OSPF version 2 and you have OSPF version 3. All right, these fall into two major categories. One are interior gateway protocols and the others are exterior gateway protocols. I'm going to get a little more in depth into that, but just know that in the interior gateway protocols are more designed for they're designed more for businesses and larger networks versus the exterior gateway protocols are more designed for internet service providers. The interior gateway protocols uses a distance vector or a link state to transfer the information back and forth. And we're going to go into the differences of that as well. Versus an exterior gateway protocol is going to use path vector. So depending on your different scenario that you have, you would choose whether you're going to have an interior gateway protocol or exterior protocol. Probably if you're working with a corporation, then you're talking about more of an interior gateway protocol. And then you're going to choose whether you need distance vector or link state, if you need the advantages of link state or if distance vector is going to work out for you. And then whether you're using IP version 6 or IP version 4. And then you would choose whatever one is going to meet your specific needs. So what is the difference between an interior gateway protocol versus an exterior gateway protocol? Well, if you have your network right here, what you want to do is transfer information from router to router. That is the interior gateway protocol. So those are the interior networks, here, here, here. This could be maybe different interior networks that you have, or maybe it's interior networks between many different companies here. And then between internet service providers, you are going to have an exterior gateway protocol. So these are the exterior gateway protocols that are going to operate between these networks. And so many different ISPs are out there, and when they interconnect, they're interconnecting with an exterior gateway protocol. As we saw in a couple slides ago, interior gateway protocols have either distance vector or link state, and you're going to have to choose which one is going to be best for your network. So we also mentioned that exterior gateway protocols uses path vector. We're not going to get in depth into path vector. It operates quite a bit differently than distance vector and link state. So with distance vector and link state, the differences are here is, first of all, from a design perspective, a distance vector is much more simple. It's passing the whole routing table from one router to the next. Versus link state is a little more complex. It's sending a lot of little bits of pieces of information about each one of the links, link state, each one of the links on that network. So it will label the links and then send information of those links to the other routers. So that is the difference between distance vector and link state. So for an implementation standpoint, distance vector tends to be easier to implement because it's much more simplistic in how it operates, versus link state tends to be a little bit harder. Distance vector tends to have less features involved, whereas link state tends to have more features that are involved. The distance vector tends to have less bandwidth usage because there's less updates that are being sent back and forth, versus link state has a lot more smaller pieces of traffic that's being sent all the time. And so it tends to be more chatty, it sends more information. A distance vector bases how to get to these different networks based off of hop count. How many hops does it take to get from destination to the final destination, to the final network? Versus link state uses the shortest path metric. And so it creates a cost of how to get to the end destination, and then based off of that cost, you're going to choose the best route. Distance vector, for each router, does each router have a global view? And so distance vector, no. So all it's seeing is just kind of where do I send it to get closer to that end destination? Versus the link state has the whole picture in mind. This is kind of like the difference, I'd say, between like if you print out instructions to get somewhere, or you have instructions to get somewhere and they're listed, well, take a right at this gas station, take a left to get onto the freeway, and they're all printed out in words, and versus you print out a map and now you have multiple routes to get to the end destination. The infinite count problem. So this can have routing loops when it comes to distance vector, versus link state can deal with those a little better. Some example of this is RIP is an example of a distance vector, OSPF and ISIS is an example of link state. Notice I left EIGRP out. EIGRP can be considered more of a hybrid. It really is distance vector and how it works, but it has a lot of extra functionality and has a lot of quite a few advantages of the link state as well. So think of EIGRP as being a little more of a hybrid there. This distance vector is designed for smaller networks and networks that have similar bandwidth. Because the metric is hop count with it, then all your links need to be similar. Otherwise, it can't take into account the bandwidth between two different links. Versus the link state can, and it's built for larger networks with dissimilar bandwidths. The algorithm that it uses, the distance vector tends to use Bellman-Ford, versus the link state tends to use the Dijkstra's algorithm, and we are going to get more in depth into that as well in a future video. So why would we choose one over another? Well, from a convergence speed, that means convergence speed is how fast these devices communicate, and that a router in the network gets the full view of what's going on, of where it now knows all the best routes to all of the networks. So from a convergence speed, distance vector tends to be slower because it's sending all the information about the routing table from router to router. It's a lot of information to pass off all at once. Versus the link state tend to be faster because it's sending out just bits and pieces about each of the networks, each of the links. It's the link state once again. So each of the links and the state that they're in. From a scalability standpoint, the distance vector don't scale well. There's a limit to how big those networks can be, versus link states do scale much better. And remember, EIGRP is kind of that hybrid that's in here. Resource usage. Because distance vector doesn't have a lot of information that's being chatty all the time, it just needs to send a few updates now and then, and there's less processing that happens, so there's less CPU usage, it's less information, so there's less data that's being stored, so there tends to be lower resource usage, versus link state tends to have a higher usage involved there. And then from an implementation and maintenance standpoint, distance vector tends to be simpler, and you don't have to be able to change as much or do as much configuration to get it to work correctly, versus link state can be more complex when you're implementing it. So let's look at a few highlights of some examples. Here we have RIP, Routing Information Protocol. RIP uses a metric, so the metric is what it's determining is the best route is based off of the metric. And it uses something called hop count. So every hop that it takes, every layer 3 device that it hits between that router and the end network, the destination network, is considered a hop. And so it'll just count those up, and then you come up with the metric of hop count. So if it takes 3 hops to go one direction and 5 hops to go another direction, then it's going to take the route that only has 3 hops to get to that final destination. This works fine as long as all of your links have the same speed to it. But perhaps that 5 hop actually has faster connections with it. Then that would actually be a faster connection, even though RIP would choose the 3 hop count. So in that case right there, maybe you choose something like open shortest path first. Open shortest path first uses cost as a metric. So what it's going to actually do is it's going to get a little more sophisticated with its calculation. It's not only going to take a look at the hop count, but really it's looking more at the bandwidth and the bandwidth of all of the links between the router and the final destination, the final route that it's going. And so it'll plug that all in there, and it will then choose the faster links and send it across the faster links. So faster links equals lower costs equal better, and so therefore that is what's going to get chosen. Then we have Enhanced Interior Gateway Protocol, EIGRP. And so its metric is cost, so it does use bandwidth as a calculation, but it also uses delay values. So it actually can see if there's delays, and it can actually use a couple other things as well. It can use reliability and load to choose what is the best route to get to the final destination. So we're going to be talking, in this chapter a little more about RIP and some of the advantages of RIP, and we're going to get in depth into OSPF and what the cost is, how to calculate that. So a good portion of this is going to really focus on OSPF because that's primarily what you're going to see on the CCNA. In this video, we talked about dynamic routing protocol types. We started out with the table that shows a broad overview of the different routing protocols and how they differentiate themselves from each other. Then we got into what is the difference between interior versus exterior gateway protocols. Interior gateway protocols being more designed for companies and large infrastructures versus exterior protocols would be more for internet service providers and the internet. And so that's where we would see the exterior gateway protocols. Within the interior gateway protocols, we have both distance vector and link state vectors, and these smaller networks we would want to use more distance vector versus the bigger networks we'd probably want to use more link state. And there's a few other decisions that we would make on choosing whether we want distance vector or link state. And then we gave some examples between RIP, between EIGRP, and OSPF. Now, moving forward, we'll talk a little bit about RIP, but mainly this module is going to be about OSPF because that's what you'll be tested on when it comes to the CCNA certification.